All right, good morning, everybody. So I am going to do today an updated tutorial slash SOP slash whatever you want to call it about PFIB lamella prep because the old one was a couple of years ago and there's been some, additions to how I kind of do things and some of the, the procedural aspects and whatnot. Obviously, there's so many different ways and approaches to making lamellas. I mean, hopefully this will give you some ideas, but please don't think of this as absolute. But I did want to do an updated one because, there have been some changes to the way I make the lamellas compared to what I was doing back in late 2022. So anyways, I have my system already back under vacuum. Let's take a look here. So this is our test sample. It's 111 silicon with 200 nanometers of chromium. And I have to have a grid over here in the grid row holder. So let me move. My vacuum is back. I'm just going to move the sample up to near eccentric height, which is 4 millimeters working distance. Again, the display doesn't normally look like this. It looks like this because of the screen capture that I'm using, but normally it doesn't look like this with the images not expanding to take the full quad frame. All right, that's good enough. So I'm going to put my SEM voltage to 2 and the SEM current to 6.4. This is going to work for the initial PT dep with the SEM. And then for the ion beam, I'm going to put that at 12 and 0.1. And you're going to see why. But, the first thing we're going to do with the FIB beam is we're going to do a PT strap on top of the SEM PT. So then for each of the beams, we want to zero the beam shift. So you can come over here in your beam control module, you can right click on the beam shift crosshair and click 0. Alternatively, you can go to stage and beam shift reset. You can do the same thing here, 0. Or you can come up here, beam shift reset, but you have to activate each quad. With the with the FIB quad, which we have activated now, I like to have the scan rotation set to 180. So it's already set here. You can see if this was on 0, you double click on here and then you can type in whatever you want. So this is a stylistic preference. This maintains top-down orientation in the FIB image. You do want to couple the mags. So that just ensures that your horizontal field width is the same in both the SEM and the FIB image. As you get more advanced, you may find that this is, something that you can do without. Even to this day, I prefer to have this, even after having, used these microscopes for all this time. And so from there, we are ready to wake the system up. So I'm going to activate the SEM quad and hit wake up. So that's going to turn on both of the beams. So you can see I have beam on for the SEM, beam on for the FIB. And then the nice thing with this system is that it starts heating the GIS immediately once the vacuum is back. So we don't have to do anything there. iSpy is on right now. I'm going to turn that off and we'll talk about that a little bit later. All right. So let me unpause the SEM image. So you can either left click on the pause button here, which is nice, or here in the toolbar, or you can push F6 and that will start it. And we can't see anything. So we'll do auto contrast and brightness, or you can do F9, or as I like to call it, black and white cookie. All right, so we've got a few marks already here on the surface that we can use to help us focus. So these are old, what are called shower drains that we use for doing the automated PFIB alignment. The center cross is not on here. If you do Shift F5, that turns it on. Alternatively, you can go to View and you can check center cross, which is already here. Okay. All right, so now that we're focused, we can hit the UFO question mark button, go to the navigation tab, and we're close to 4 millimeters, but we'll go ahead and move straight to 4. And let's check the crossover. Okay, so that's centered reasonably well. The zoom here changes the magnification of this, and then you can click and drag on source tilt crosshairs to center this. Obviously, that's no good. You're not going to see anything. If you can't see anything, it's probably because this is off. You can change the sensitivity here. Okay, and then I'm going to hold off on doing any further alignments till we've mechanically set eccentric. So, well, I guess before that, we could set, let's go ahead and set eccentric here, and then we'll talk about aligning the sample after that. So anyways, we move to 4 millimeters. I'm going to tilt to 26 degrees. That's half of 52. And the sample moved down, so now we need to move the stage up. So you can click the right arrow. So the stage on this system it's a good stage, but it's entirely mechanical, and it's not the most precise with its movements. So okay, now I'm just doing single click. That looks good. And now we're going to tilt back to 0. And then we're going to tilt straight back to 52 degrees. So, I tried actually making this video on Friday. I think if you saw the video I did on FTEM, I told you Friday had been kind of rough for me. I tried making this video on Friday with a different material, and it didn't work well. So I said, okay, I'll do this again, but I'm going to do this with just silicon. All right, so I refocused, hit the UFO button, so this relinks after you refocus, and then we can tilt straight to 52, and we should see minimal movement or less movement here. But if there's still any, we can carefully bump this up. Okay, so there's a little bit there still. Okay, and then back to 0. Okay, so this is a single crystal substrate, and as a result of that, it has certain cleave directions on it. So this is a 111 wafer. So the cleave edges here, these are 110 directions. So if we cut perpendicular to the cleave direction, that's going to the view direction in the STEM will be 110. If we cut parallel to this, the view direction is actually going to be 112 family. Okay, so keep that in mind depending on what you want to do. So what do we want to do? Well, we need to find a cleave edge first. So let's mag out here, and actually let me come back here, and we can double left click on the cleave edge. Okay, so there's the cleave edge right there. We see the nice vertical line here. So you can go to stage, align feature, pull this over. And if we pull this down, okay, so now if we align horizontal, it's going to rotate this so it's horizontal. If we do vertical, it's just going to, so it's just going to go 2 degrees. So it's going to look like that. So then this would be for cutting this direction. I'm going to cut it the other way to give us like a resolution check sample for 200 kV on the Themis, because the dumbbells in that case, those are 78 picometer spacing. So now from this point, I can do the same thing here. I can click and drag and then just tell it to do 90 degree, or actually tell it to do horizontal rotate. Now I have it set to do what's called safe stage moves, which I'll show you here in a second. Okay, so up here in stage, there's an option for this enable safe stage move. So when you do like a big rotation like that, it's going to back the Z down a little bit. So then when it rotates, it's not going to hit anything, or it's in less danger of hitting anything. Okay, so at this point, we are ready to find a spot on the surface to make a sample. So we'll go ahead. And actually now, as I mentioned, we can do the rest of the alignment here. So we can come over here to direct adjustments, turn on lens modulator, and now I like this around maybe 0.4. And you can use your crosshairs here. You're trying to minimize the shifting of the image as it goes in and out of focus. Okay, that looks pretty good. The horizontal crosshair, this adjusts the up and down shifting, as you can see. It's best to adjust these one at a time. That looks pretty good right there. Okay. What you can also do here, I have 300 nanoseconds. At this current, you get a lot of signal to noise, so that's fine. But if it helps you, you can turn on reduced area here. I don't know why this is at a higher pixel resolution, but put this back down, and then you can usually bump this up to like 3 and do the same thing. Okay, and since it's a smaller area, even though your dwell time is higher, the response is still relatively fast. So anyways, you can do that if it helps you. At this high of a current, I don't find the need to do this, but it's just an option. All right, and then the last thing is to stigmate. So you can use your stigmator knobs that we have on our MUI if you have a MUI knob set. Otherwise, you come to beam control and you can activate them here within the stigmator panel. Okay, we actually do have a microscope that doesn't have a knob set, and that's what you have to do. You have to actually activate them there. So our wafer is relatively flat. So even though I didn't set eccentric here, I'm going to assume that it's close enough, and we're going to put the strap down. Okay. So I'm going to move away from this crud here, and I'm going to put in my platinum. Again, I'm only doing this because I have a nice flat sample, and I'm going to go ahead and draw a box. So application, whichever you're using for platinum E-beam, and I'm going to do 12x by 1.5 for the Y by 0.5 for the Z. And I'm going to open up the flow here. So we're going to put down some initial platinum just in the vicinity. And you can actually, I have this actually as a preset here. So you do have presets patterns for each beam. So you can have up to 6 for each beam. So I actually have this already here for this beam. So you can see if I do preset 1, it's drawing the exact same thing. All right. And we'll go ahead and start. Okay, so you'll notice I have not done any ion beam exposure to the area yet, okay? And that's by design. So you don't want to do any ion beam exposure until you put down this initial SEM assisted strap, okay? Because that's going to ensure that everything under the strap is still unadulterated, okay? If you did ion beam exposure, you would be damaging, right, what's the near surface area. Now, if you have a protective coating already on it, that may not matter. If you're not concerned about what's happening right at the surface, that also may not matter. But a lot of the time, that is the case. We're concerned about the very near surface region, so that's something that we want to do. So when you're doing PT dep with the SEM, the process actually, whether you're doing SEM or FIB assisted, it's dependent on secondary electron generation. So you usually want to use a low beam voltage for this. So the recommended voltage is 2. So it's a good, trade-off between probe size as well as secondary emission, because as your voltage goes down, you tend to generate more secondary electrons, but obviously your beam gets larger as well. So your deposition becomes less precise. And then as far as the current, so more is better here as far as the SEM is concerned, right? So we don't have to worry about sputtering of the material when we're doing this. So, using a high current here is only going to help you in terms of making the deposition efficient. Obviously, the trade-off, though, becomes the size of your beam, right? So as I increase the current here, my probe size is going to be bigger in the SEM, so my deposition may not be quite as accurate. So, but for what we're doing, we're just putting down a strap of this dimensions. This is perfectly fine. Okay. And we'll remove that. We'll delete this. And there we go. We got a good looking strap. Okay, so now I'm going to tilt here and we'll see. So we're a little bit off here. So we're going to reset eccentric. Okay, and we'll do one more iteration. And then we'll go straight back to 52. So you can see the area that we were scanning initially, there's a little bit of a pile up here. That's because of the way the scan works. So it goes from left to right. There's like a little pause there, so you get this little build up here. And I guess we can bump up the Z just a smidge. Okay, that's good. All right, so we won't worry about, well, we can stigmate this a little here. All right, so now we're going to go to the FIB and unpause this. And now we don't have coincidence here, so we need to shift. So we're using the shift knobs on the knob set. Alternatively, you can find your beam shift crosshair, and you can adjust it here. You can see how this works, right? Your other option too, if you hold down shift and then left click and drag, you can do this as well, okay? So the actual ion current is down here. It's about 92 picoamps. You can very quickly just see if you can't focus. I mean, the default looks pretty good here. And then I'm going to put in the platinum again. Okay, open it up. And I'm going to draw a box with the same dimensions that I just had. So it's going to be, but now I'm telling it to do ion beam depth. So it's going to be 12 by 1.5. And we're going to do 1 micron. So again, I already have a preset for this. This is preset 1. Okay, take a snapshot. That looks good. And we'll hit play. All right, so why these dimensions? So based on the current, right, 92 picoamps. So if we do a little math here, okay, if we do 92 divided by 1.5 divided by 12, that gives me 5.1 picoamps per square micrometer, okay? So the important point here is the current density. So you want the current density to be optimal, and somewhere around, I think the tech note says 2 to 6 picoamps per square micrometer. In my experience, you can go a little higher than this to maybe like 10 or even exceed that a little. But if you go too high, you end up milling the material instead of depositing, okay, which you obviously don't want. And if your current density is too low, then your deposition rate is just very slow, okay? So that's why I chose those dimensions based on the current. If you had a set dimension, right, and you only have so many currents, well, then you would have to then decide, well, which one would I use? So usually you want to use, I mean, you have to look at which one is closest within that range and then go with that. I think the the instructions are usually to err on the low side if you have a choice between going high or low, because obviously we can't, dial in whatever current we want. The choice of the voltage, so that's unique to the PFIB. So empirically, it's been found that reducing the voltage to 12 when using the xenon produces a better result than at 30 kilovolts. Again, that's unique to the PFIB. We don't see that issue with the gallium. And again, that's for doing the strap. So when you're doing things like welding the lamella to an easy lift or the grid with the lamella, then that's a little less critical. But for putting the strap down, then you definitely want to do that. We can go ahead and unpause this here. So I had iSpy unchecked. So when we unpause this, it's just going to show us, what's going on here. So we can see the strap go down in real time. Okay, and we can actually, there we go. So your astigmatism doesn't stay good forever, or your stigmation adjustment doesn't stay good forever. And this is, one of the more time-consuming steps here. So this is a good time to go to the bathroom, go get something to eat, right? Take a break while this is happening. Some of these systems have on them what's called a multi-chem, where you can actually flow carbon and platinum at the same time. We do not have that on this system. I've heard that works very effectively in terms of producing a strap that can be kind of superior to either one of these. So I haven't had much luck with the carbon. Granted, I haven't played around with it a lot. The big problem I have with the carbon is that, well, one thing is you can't plasma clean it, right? So when you put it into the microscope and you try to plasma clean it, the plasma will attack it. Okay, will not do that with the platinum. So we get fairly consistent results with this approach. I know in the previous video I was using like a much higher current density when I was doing this strap before, so I don't do that anymore. I'm way more conservative now with this. But don't worry, the next few steps, so we're going to, after this, cut trenches and then do coarse thinning and then J-cut and then lift the sample out. So that should go a little more expedited, at least hopefully. Well, that's happening here. Let me look through my positions. We can get rid of this. We can get rid of that. All right, so we got a good looking strap going here. So this SPY mode here, what this does is intermittently it acquires images with the SEM. So instead of doing constant live imaging, it's doing periodic snapshots. This can be done specified on a time interval, or if you're using a cleaning cross section, which takes slices, it can be done on a CCS line interval. Okay, so I like actually using this when I'm doing cleaning cross sections, but not so much for something like the strap deposition. So, or with the trenches, which is what we're going to do next. All right, we're almost there. So we're at 52 degrees now, and I'm going to deviate from this for the next few steps, plus or minus 5 degrees. That's going to help to taper the lamella toward the bottom as well as preserve the cap. Okay, so I'm going to start by over tilting. So that's going to be 57 degrees, and then I'm going to under tilt 5 the other way. More is better here within reason, but obviously you have a limit based on, your stage, right? So you don't want to smack into anything. All right, we'll take out the strap, and now my voltage is going to go up to 30, and I'm going to go all the way to 60 nanoamps, and I'm going to tilt now to 57, and now I'm going to mag out to about let's see. Yeah, we'll go with 1,000. So this is very low mag here, and so when we take a FIB image, right, because we have high current, the current density is going to be low. So let me go ahead and take a snapshot with the FIB here. Okay, so that's actually not too bad. So this can be tricky. You can do auto contrast and brightness, but this was actually, reasonable here. But you want to minimize the amount of live imaging when the current's really high like this. So we're going to go now to a regular cross section, and I'm going to make it, again, we want this on silicon. I'm going to do 20 wide by 10 tall and 10 deep. And you see there's a thick line. So this is the deep side of the trench. And since we're over tilted and the scan rotation's 180, the lamella or the PT strap is actually pitched downward, so we want to cut from the top. Okay, so we can change the scan direction from top to bottom. Alternatively, you can change the rotation here, but it's kind of quicker just to do this. Again, I have a preset for this, so preset 2 draws the exact same thing. Okay, and again, you can modify this however you want. All right, so we want to put this centered here, and I want this about 1 strap width away. Okay, something like that is good. Okay, but you don't want this too close because your beam is pretty large right now. All right, and with that, we want the scan method also on multi-scan. So I'm going to talk about that as it goes along here, and we'll go ahead and start. Okay, so this is set to do what's called a multi-scan or multi-pass here. So basically, there's 2 approaches to the regular cross-section. There's the multi-scan / pass or the staircase. So the staircase is actually easy to explain. So basically it cuts like 5 steps for the trench. Okay, so each step is a little bit deeper than the next. The multi-pass basically starts with the beam at the thin end of the pattern, and then it slowly snakes it along to the thick end, and it gets a little deeper as it moves. So the advantage of the multi-pass over the staircase or the stair-step approach, I find, is 1, it produces a cleaner trench with less redeposition, but it also tends to cause less wearing of the strap as well. Okay, so that's why I tend to prefer that approach than the stair-step approach. The other thing too here, this is important, is this parameter called the overlap. So this is I have set to 85%, which I find works well for silicon. The default value for this when we got the system was actually set to 50. And we found that was just, it was too low, just wasn't producing good results. All right, so I'm going to tilt 5 degrees the other way. It's under tilt now, so that's 47. Okay, and now I'm going to reverse the scan direction, take a snapshot. Okay, and then same thing. So I'm going to position this from the bottom. Okay. Okay, and then we'll go ahead and hit go. All right, so the overlap. Okay, so the overlap specifies literally how much overlap there is of the beam between adjacent points in the pattern. So if the beam has a certain diameter, the overlap of 0%, for instance, would mean that each beam spacing, there is no overlap between the beam. Okay, so if you can imagine, right, the beam is a circle projected onto the surface, so the circles are just touching each other on the edges. Okay, there's no overlap of the circles. If I had a 50% overlap, then the edge of one one circle would be in the middle of the adjacent circles. Okay, that would be 50% overlap, right? Because that's half the diameter, right? So that's what they mean by overlap, if that makes any sense. So we have this set to 85%. So, and we found we had to do this because at 50%, it wasn't removing material effectively, and it was giving us a lot of curtaining. So 50% on the gallium tool tends to work a lot better, but we've empirically discovered needing to do this with the PFIB tool. Okay, so we're going to tilt now to 57, and we're going to drop the current to 15 nanoamps. I'm going to mag up to 2000, and I'm going to take a snapshot again. Okay, that's good, so I'm not going to do any more auto contrast, and now we're going to go to the cleaning cross section. And same thing, silicon 20, and let's do top to bottom again. And so we want this right about here, right next to the strap. Pull this down. And we can drop the Z here because we're milling the sidewall here. So the depth doesn't work quite the same way. Again, I have preset 3. Does the same thing. Now we have to fudge with the Y here, but everything else is exactly the same. Okay, so we'll go ahead, pull this up right here. Okay, so now here's where we're going to turn on SPY mode, and this is going to take basically a snapshot after each slice. Okay, so that's what the cleaning cross section does. Is it takes slices starting with the thin end, and it moves a little closer, takes a slice, a little closer, takes a slice. Okay. So whatever your dwell time is here, now I had the image live, okay? If I pause it, it's not doing it. So then I have to unpause it, and then it goes back to doing iSpy. So if I change this, that changes the dwell time used for the snapshots. I'll just leave this on 300 here because we got good signal to noise. Okay, so if we do this right, we shouldn't really be hitting into the strap here. We could probably do this a little bit more. So I'm actually gonna move this up a little bit. I'm gonna run this again. See if we can't dig into the strap a little bit more. Okay. There's some redep on the side, so we might see that kind of fly off here. Yep, okay. All right, we got it a little bit better. So, all right, we'll leave it there. Okay, then we'll tilt to 47. And I'm going to take a snapshot here with the FIB. We'll reduce or reverse the direction. Just down here. Now with this direction, we can't actually see the cut face here. So we have to monitor this by looking at the back side. Okay, so this is the side we're cutting. Okay, is the side we can't see. So we can watch as the silicon gets thinner here. So we can see as it kind of gets near the edge of the strap here, you know, that can be kind of our litmus test for when to stop. I'll keep my finger on the stop button here. Okay. Okay. I think that's good enough here. Let me tilt to 7 degrees. Okay, that looks good. All right. So at this point, we can go ahead and set up for the undercut. So we want to be at 7 degrees for this. That has the fib beam at 45 degrees relative to the sidewall. And I dropped to 4 nanoamps. So we can go ahead and unpause. Okay. And now we want to draw our J cut. So I do have a preset for this here, P4, but let me show you how to do this anyway. So you're going to click and drag here. You want to use just a rectangle here. So let's start actually with the bottom here. So with the bottom, you don't want to go all the way to the bottom of the trench. Something about like 1/3 from the bottom should be okay. And then we want to put one on the side here. And then we want to have overlap in the corners. And then same thing here. Oops, let me mag in a couple. That should be enough there. Let me take one more snapshot. Okay, so let me move. Okay, and we do select all. We can change this to something large, right? Because we're going to monitor this. And we want to set this to run in parallel. So it runs all these at once. Now, if you want to change this, any one of these, just deselect it and then you can fudge with the boxes, okay? But this is what you want here. So let me go ahead and, because the default may not fit this perfectly, okay? So let's go ahead and start. And now with this, we want to turn iSpy off and just monitor this in real time. We can turn on an averaging filter here. You can do this actually now inside the FIB. So if you unpause it, we're seeing the live FIB signal from in the box here. So this is good to verify the undercut mainly, but it works well for the other stuff too. So usually the corners clear out first. Okay, we're starting to get some wear here. Now we're going to see a little bit of bowing on the bottom here. So that's the opposite side that we're not seeing in the fib. And so we can clean that up when we're done if we want, or we can just go straight to mounting the lamella. It doesn't matter because we're going to have to do it one way or another, so we're not really saving time if we just skip it now. Okay, so we can see, yeah, clearly we have those holes here. This has to be all cleared out. So we're just going to leave a little bit of a nub right here that the lamella is hanging on to the bulk by. Okay, and we're almost done right there. Okay, so this side is through. That side is through, so now we're just waiting for the bottom. Turn up my contrast here. And yes, if that bottom is not cleared out, then we're never going to get the sample out. So we got to make sure that that cuts through. We usually see it's kind of like a zippering almost here, where it kind of like opens up. We'll see like a light line up here at the top once it cuts all the way through. Sometimes you can see it in the, yes, we're seeing this bowing out here, so it's getting close. Okay, yeah, so you can start to see, yep, there's a little bit of, yep, dark area in there in the undercut. Yeah, last time when I did this live imaging with the FIB didn't work as well. We had a problem with the detectors. This is now using the ice detector. Before we were doing the ETD and that had problems with this not working, but we don't have that issue now. So now this works perfectly. Thank the service technician for that. All right, so that is through. All right, so we're good. So we can see here we have this kind of bowing out here. So let me turn off the averaging. I can do preset 1 here. Yeah, so let's go ahead and clean that up. So we're going to tilt back to 57. Turn this off. Turn on the crosshairs here. But yeah, you can see the undercut there very clearly. All right, and we're going to draw a cleaning cross section, top to bottom. We'll do 5 there. Okay, and here we go. We could probably cut the Z a little more here because, again, we didn't go all the way to the bottom of that trench. You can see the other side of the J here, which is good. When you do that left side of the J in the FIB, which is the right side here in the SEM, you want this, I mean, we could have got this a little closer. If this is too low, sometimes that can have an issue in terms of cutting this through all the way, but this should be okay in my experience. Okay, so we're starting to see the undercut here come through. All right, so we're almost done here. We don't have to run this the whole way. Okay, that's good enough. All right, and so at this point, we should be ready to pull the sample out. It's nice and cleared out. I'm going to drop my FIB current to 30 picoamps. Yeah, so this is ready to go. Okay, so we have averaging off here, so we're nice and live here with our images. Okay, use my shift knobs to center this, and all right, we're ready. So we'll go to the easy lift module and click park position. Okay, there it is. This is about 200 microns above the surface. And then we're going to go to patterning, we'll turn off SPI mode and insert platinum. Okay, and now we're going to approach the easy lift. So if you're careful, I mean, for a new person, I'd say just do jog and leave this on 10. Okay, I wouldn't try going higher than this. So negative Z, this is moving it down in the FIB image. This is why I like the rotation, scan rotation at 180. Otherwise, when you hold down, that corresponds to the easy lift moving up in the image, and that can be a little confusing for some people. But again, matter of preference. Okay, once it gets kind of close here, I'm going to mag up a little bit more, and I'm going to insert or open the flow to the platinum. We'll switch to, and then we'll switch to 1 micron a second. So really you only need two speeds here, the 10 and the 1 micron per second, and that should be enough here to do what you need to do. Let's go ahead and draw the pattern here. So we have that ready, and we're going to snake this or sneak it just along the side of the lamella here. Okay. And now it doesn't have to be in contact, a little bit of a gap, like that's perfectly fine right there. So go ahead and leave that, and we'll put that right there, and we'll hit play. Okay, so now we can watch this in the SEM here. So we're going to see the glue fill up the gap here. And that's plenty right there. So we can stop. Okay, we're going to put the current up to 1 nanoamp. Change our pattern to silicon, keep the rectangle. And now we have to cut the nub here. So again, adjust this up and down, left and right as needed. Hit play, and we can watch it here in the SEM image. And if everything works okay, when this is free, we should have a nice floating lamella. Okay, I'm going to drop my current down to 10. Yep, and it looks like it's shaking a little, so that should be good. Okay, and we can go up with the Z. Yay! I want to get this so it's out of the trench a good ways, and then we can take out the platinum. Then we can put this in park, easy lift, park, go to, and then retract. Okay, I'm going to pause that. All right, I need to take a break here for just a couple minutes, and I will be right back. All right, need to head over to the grid. I'm going to store a position here in case we need to come back. So I have saved positions for all the grids, and I believe I've got a grid here in the 4 position that I've labeled it. So we'll go to right here. Okay, I think there was another one here. Okay, there we go. Yeah, so this is a 4-post one, so I'm going to use this one. It's a little bit thinner. Wait a second. That's already got stuff on it. I know I put a new one in here. See, these I've already cut. Well, if we have to use that one, we will. I thought I had a 4-post one in here, but I don't. Okay, well, we'll have to use one of these. All right. So this is a 2-post grid here. Okay, so these are both notches, and these are on the thick side. This is molybdenum here. So we're going to have to do some additional prep here with these. So first thing we want to check is, is the grid edge on? Are we looking at it edge on? So it looks pretty close here. If I go -1, see, that looks worse. If I go +1, so if I do 0, that looks pretty good. So we can just leave it at 0. Then we want to check the left to right twisting. So again, if you do stage align, you can use this top edge of the grid here. So it might be off just a smidge horizontal. Okay. And then we're going to tilt. Okay. And actually, I'm going to, all right, we're 52 degrees. So that's, parallel to the ion beam. I'm going to back this off by 2 degrees initially here because we're going to do some additional prep to the grid here. So let me go live with the ion beam or the FIB beam. Okay, so what we're going to do here is we have to make sure when we attach the lamella that we give clear what's called line of sight. And so if we don't, then we're going to have problems, okay? So the way to do this is my preferred method anyway, is we have to clear out the bottom half of the grid, just completely remove it, okay? So why don't we, that's 2 degrees, if we tilt 1 degree instead. Do we want to do 0? All right, let's do 52. Okay, we'll do edge on, that's fine. We'll leave it right there. Again, the thin line is the start, the thick line is the middle or the end. You want this about in the middle of the grid. And we're going to go all the way up to 2.5 microamps. That's where the utility of this PFIB really shines here. And we're going to cut 20 microns deep, okay? And we're going to use the SPY mode here to monitor this. I'm not going to take a live image. I'm just going to assume my beam shift is, excuse me, accurate enough for what I need to do, which it should be. And let me go a little bit more here. Let me do 25 just to make sure. And there we go. So it's inserting this blocker here when it does the FIB milling to prevent, it helps to prevent crud from getting up into the SEM column. Excuse me here. Having a snack while we're doing this. So I changed the interval to 3 CCS. Or 3 lines, I should say. So the idea here is we want to make sure that there's nothing in front of the grid. Okay, we have to make sure we have clear line of sight when the grid is mounted, when we put it in the microscope, okay, or else that's going to be a bad day. We go to all the trouble of making the lamella and then we can't see it. So, and we don't want that. We're going to let this run a few more of the lines here. Obviously at, 2.5 microamps, your beam is not constrained to just here, right? Keep that in mind. All right, that's good. I'm going to drop this current back to 10, and then we're going to tilt back to 0. 0 being norm or parallel to the SEM. Obviously, if this was minus or plus 1 degree, we'd have to do that instead. Okay, this looks good. Right, we cut about half of the front part of the grid. All right, so do F9, and now we're going to do the same thing, but we have to come from the top here. Okay, so one thing we can do to help expedite this is we can make a polygon. So I'm going to click. There's one. Okay. And the Z, we'll do 10, whoops, select all. We'll do 20, and we'll just monitor this here. We can monitor this actually in the FIB. Okay, so we'll go ahead and start. Oh, this is set to parallel. Sorry, let me set it to parallel. Okay, there we go. So we're trying to get rid of the rabbit ears here. Take a snapshot here. We don't have spun. Well, I didn't unpause it, so that's why that's not on. I'm gonna just unpause it, take a snapshot. Yeah, so it's working. So this would be very hard to do with the gallium tool because your current maxes out around 65 nanoamps. So do the math, it would just take a long time. Okay, we're getting warmer. All right, so that's good enough. I'm going to switch to the cleaning cross section. And let's do 10. All right, and then here we go. So this spot in the middle is, depressed still, and right here on this edge is where the sample is going to go. So this has to be flattened, okay? And so this should be pretty obvious when that gets to that point. All right, so now we're going to polish this up a little bit more in the middle here. Because that's a little bit rough. And we're going to go to 60 nanoamps. And we can actually live image here, so no problem there. We're just imaging the grid. All right, so we'll do 40 wide. Remember, the lamella is only about 12 microns wide, okay? So this is, this is plenty of width here, right? The actual lamella is much, or not as wide as this, okay? All right. But now this is going to give us nice, perfect line of sight here, okay? Lamella is going to go right here on this edge. And the person I trained recently had a very good analogy. She said this is like being on the peak of a mountain, right? And it's perfect, right? So unless you're on the peak of the mountain, some part of the mountain could obscure your view of everything else, right? The only way to ensure that there's nothing obscuring your view is to be on the peak, okay? And so that's what we're doing, is we're making the peak of the mountain right there. And now we should see this smooth out here. So I have this set to 3 for the interval. Let me put this back to 1. Okay, it's looking good. Doesn't take nearly this much work with the 4-post grids because those posts are narrower, but they're also thinner. So these 2-post versions, they're on the thicker side, and they require a little bit more time in order to prep, but that's okay. I had one in here that was already prepped, but I didn't want to just, do that, right? I wanted to show you what the prep was. I know I did a video on that before, but I wanted to give you a cradle to grave demonstration here about making a lamella. And this is looking good now. Nice smooth surface here. Okay, looking good. Great. All right, we're going to increase or decrease the current to 30, which we'll use for doing the weld. Okay, and since we're at eccentric here, we can go ahead and put in our easy lift, and then also go ahead and put in our platinum Turn off spy mode here. Okay. And we'll go to 10 microns a second and negative Z. I've often said we should have a contest with the easy lift to put it on the fastest speed, and you get to hold Z down and see how close you can get without letting Z go, or before you let Z go, right? Call it the easy lift Olympics. All right, let me use the shift knobs to shift this up a little bit. You don't want to use the stage at this point. You're going to risk dinging something. Let's open up the flow. Same thing with the SEM. You can use the shift knobs here. All right, so we're going to move this so it's over. We want it centered in that flat area, and then we want this basically right up next to the edge. Now, it doesn't have to be perfectly, but something like this, okay? This is right on the peak of the mountain. All right, and I'm going to go ahead and draw my pattern here. So our current is 35 picoamps. So again, if we follow the current density rule, so if we do 3.3 by 3.3, so if we do 33 divided by 3.3 divided by 3.3, that gives us 3 picoamps. So that's a good current density for what we need to do. Okay. All right. So now this edge is actually lower than this, because you have to remember we're looking at this with the FIB beam. Okay. So it's going to look like we're going to smack into it, but I assure you we're not. Whoops. So don't do that on me. Okay. I'll see if I can drop this anymore. Okay. So now it doesn't have to be touching, just a little bit of a gap there is enough, and in some ways can even be kind of preferred. And we can actually cut this down a little bit more here. All right, so let's do that. It's going to increase our current density slightly, but again, that's okay. All right, let's go ahead and hit play. So this is the side we're welding here. So we want to see a buildup on the front here. There isn't really a number we're shooting for as far as the depth. It's just a matter of, we want to see a buildup here, right? We can unpause this too. Yeah, so we're seeing it there, which is good. If you wanted to target a depth, I'd say at least 0.2, just to be safe. There's a point at which you have, some diminishing returns. All right, I think that's good though. It's 0.25 for the depth. Now we got to do the other corner. Probably could have got this a little closer, but that's okay. We can see the buildup over here, so we're getting close. And we'll stop it at 0.25. That should be enough. All right, 1 nanoamp. Keep the same pattern. We'll just fudge with it here. Okay. And there we go. All right, so we should see this move away. You want to be a good user and make sure you leave a nice clean probe tip for the next person. Don't leave residual platinum crud there. And then we'll do the final act, which is the final thinning. So that's where there's some pretty noteworthy deviations from what I was kind of doing before. Can we see in here? Yeah, there's still a little bit of a should be close. Yeah. Okay, so that is cleared. Lamella is still standing, so that's a good sign. All right. Okay, so from here, we can just, well, just to be safe, I'm going to move the stage down here. And then I'm going to put the easy lift in park. That way I know it's not going to hit anything. And then retract. And take out the platinum. All right, so we're now ready to final thin. All right, so I'm cheating a little here. So the final thinning for the lamella that I attached didn't go very well. So through the magic of television, I attached another one here. It's a little bit thinner starting than the other one, but you know, it will still work. So we're gonna make some adjustments here from the final thinning. So I'm gonna start by reducing my beam current here because we want to have more accurate milling or imaging of the sample, and we don't want to possibly contaminate it. Okay, crossover spot looks okay. All right, and then we can Okay, looks good. All right, so let's make sure we still look parallel here. Basically, we'll leave it at 0 here for purposes of simplicity. And we'll tilt to 26 here. Oops, let me zero this out. Looks okay. All right, so I'm going to start by using 3 degrees of over tilt. So we're going to go 55 here. And we're going to start with 1 nanoamp, so that's okay. And you can focus and stigmate here. The stig looks okay, so I'm not going to mess with that. And we're going to use the cleaning cross section. And I'm going to be fairly aggressive with this first one because I want to see the platinum or the different platinum layers here when I do this. And we'll turn on SPI mode here. So I think I mentioned this before, but I mean, especially with the cleaning cross section, this is where the 85% overlap really helped with the result. So right now, right, we over tilted 3 degrees, so the lamella is pitched downward or tilted downward in the FIB image. We're milling the side that we can see in the SEM image. So what I'm going to do here is a neat technique that I read about in a paper. We're going to relative rotate the stage after this. We're going to keep the 3 degrees over tilt, at least initially. We might deviate from that depending on how the thinning goes. And that way, we're always milling the side we can see. So it's going to add a little bit of time, obviously, to the prep process. But the advantage of that, of course, is that we'll always be able to see the side of the lamella, make sure that it looks good. We're not getting any, faceting. We're not getting any sort of curtaining, or we can at least monitor it, right, and know that it's there, and perhaps take some compensatory steps to deal with it. The sample was a little bit thinner to begin with than what the one I ended with the bulk thinning with, or the bulk thinning was, but that shouldn't matter. We should still be okay here. Okay, so we didn't quite get there. That's okay. We'll cut it from the other side. I'm going to drop the, let me take a snapshot here. Okay. I'm going to go ahead and, let's see here. Do I want to do some more? Yeah, I'm going to go ahead and do a little bit. Well, all right. I'm not going to. I will do a relative rotate. Okay, so you go to relative here in the navigation module under stage, do 180, make sure you have compucentric rotation activated. And then if you have enable save stage moves, it will back the Z out, do the rotation. now, if this is not at the same height, you want to just adjust the stage up or down until it's at the same height, roughly, and then you can double left click to center. Okay. And we should be close here. Yes. So again, we can use the shift control to recenter in the FIB image. All right. So we'll draw a cleaning cross section. Now the issue with this direction is that what we're going to see here is we're going to be dealing with some stage drift wanting to go down, okay? So you can see, right? This is the issue we've been having with this. So we have to be a little aggressive with the box placement here, which is okay because it's drifting away. I didn't put this all the way across because that would cut through the welds and we don't want to do that. So we don't have to change the stage tilt. By doing the relative rotate, we're at 3 degrees over tilt on the other side, just as if we were, just as if we tilted to 0, did rotate 180, tilted back to 55, it would be no different. So. All right, let's see what we got here in the FIB image. All right, so we got a decent chunk here. I'm gonna cut this down, to about half of what it was. We'll run this again. There we go. One more here. Okay. All right, we'll do another relative rotate. I'm going to drop our current down to the next setting, which is 0.3. Okay, we'll go up with a Z. All right, so we got to make sure on this side that we cut far enough in to see all of the layers. Okay, looks like now you don't want to use reduced area here. If you want to stigmate on the FIB image, you can use the whole image, or you can use, if you're going to do reduced area, make sure you don't put it around the lamella, okay? Just want to make sure of that. This is the direction that is more stable. I've asked the service technician about the drift, so hopefully we'll get an answer as to why it's doing that. Okay, let's drop this down by 1. It's moving up actually. Okay. You want to stagger these so they're inside of the, the cut below, right? So what we find, or what I find anyway, with the PFIB is that we have to use higher over tilts in general than we would with the gallium, because the gallium fib, because the beam is just bigger and it has bigger tails. So depending on when we start eating into the bottom here, I'm going to compensate for that by maybe not over tilting quite as much. All right, we're getting warmer. All right, we're getting there. Might need to do another pattern after this on this side just to be sure. Okay, so we need to do a little bit more here. We'll do 0.2. Okay, I can start to see it coming in there, so that's good. Let's go the rest of the way. There we go. Okay, so we're starting to eat the bottom here. So let's relative rotate here. I'm going to do one more cut from the other side at this over tilt, and then I'm going to drop it. All right, we'll drop this to 8. I'm going to drop this to 3. There's not as much depth there. And we're going to be chasing this a little. I'm not using as long of an exposure time here because that's going to, that slows down the milling, and that's time for the drift to occur. So I'm keeping that low. It's a little noisy, but that's okay. We could just turn this off and just, live image here. Okay, let's take a look here. All right, so we singed that just enough. I'm gonna try and singe it just a little bit more. Then we're gonna drop the current, and I'm gonna drop my over tilt by a degree, and we'll go to just 2 degrees. Okay. All right, this is good here. I'm gonna stop it at this line. All right, so I'm gonna drop the current down to 100. We'll do a relative rotate of 180. I'm gonna change this to actual. And we're gonna go 54, so that's 2 degrees of over tilt now. So when I did this earlier, I was using 3 degrees throughout, and that worked some of the time, but it was interesting when I did this earlier today, it ended up eating a hole through the through the strap. So, and we don't want that. Now this is moving back. Okay. Generally, what I find is that the curtaining tends to be worse when the over tilt is higher. But again, right, it's a little bit of a trade-off here because I find that I need to use a little bit more over tilt with the PFIB because the beam is, bigger. So like plus or minus 1 degree is just, it's not enough with this, I find. I mean, this is nice looking sidewall right now, of course, and we're still at 30 kilovolts. You want to do the most milling you can at the higher voltages because, it's more accurate and your material removal rate is quicker. All right, so let's see what we got here. Okay, and we're going to do a relative rotate now. Probably should turn off my averaging filter while I'm doing this. That's okay. I like to live dangerously. All right, so we really don't have the issue with overmilling on this side because it's going to be drifting kind of away from us. All right, we'll cut this down to 6. We'll go 0.15. Yeah, so you can see it's moving away from us here. So I'm actually going to be pretty aggressive with it right there. So after this step, I'm going to tilt back the other side again, and I'm going to drop the voltage to 16, okay? So my sequence for the voltage drops is going to be, it's 30, 16, 8. Okay, and then if we're feeling, really adventurous, we'll try going 5. Okay, so I'm going to have to position the box a little bit more because it didn't really singe the side here much. Just barely did it. Yeah, so it completely moved. Okay, let's try that. I'm not sure if it does seem to kind of get less with time, but yeah, it still drifts. Like I've left it in here overnight to see, and yeah, it still moved quite a bit. So yeah, I don't know if it's just gravity working against us here. I hope there's a solution to that because it'd be nice if that would, be stable for what we need to do. We got a nice flat area here, but we still have this here, so I don't know if we're going to be able to clear that out. It may not happen considering the drift here. If it doesn't, it doesn't. Let me try reducing this 0.1, and we'll do 2 here. Okay, so that seems to be working. Okay, so we can just leave this, right? It's not a problem that we have this down here. In fact, this kind of stabilizes things to an extent. Let me take a look here and see. Okay, so we'll leave that alone. I'm going to drop the voltage down to 16, and we will relative rotate again. Turn off the average filter. Oops. All right, let me refocus and relink. Okay, so now let me switch the voltage here. What we can do, since we changed down, we can check the quad centering. So this is like lens alignment here. So you're trying to minimize the shifting. Okay, looks pretty good there. And then just like we can focus and stigmate here. Now it's not going to look as good as it does at 30 kilovolts, okay? So don't expect that. But that's about as good as I would expect here. All right, we'll drop this to 5.5. Okay, so now the depth here, again, because we're cutting a sidewall, it's kind of meaningless anyway, but especially when you drop the voltage, right? Because the depth was calibrated for 30 kilovolts normal to the surface, right? We're not normal to the surface anymore, but we're also at a lower voltage and your sputtering yield is going to be less, okay? So in principle, right, you could have a separate file for each voltage, if you were being very very ambitious, right? You could measure the yield, but again, that's normal to the surface. So your yield goes up quite a bit when you're at a glancing angle like we are now. So far this is looking good. I'm going to stop it at the end of this line here. Okay. We'll do a relative rotate 180. Okay, nice and focused. Okay. Now, if you run out of shift in the ion image after you do the relative rotate, that means you need to go back and set eccentric again in your SEM image. All right, so let's see here. Do we have enough here? Let's just do 0.12. Now again, especially at these lower voltages, your beam is not localized to the pattern, okay? It wasn't localized to the pattern at 30 kilovolts, but it's certainly not localized now. Whoops, sorry. Need to drop this down to 5. All right, let me run this a little bit again. It's probably going to just drift out of the way, but we singed that side just enough here. Looking good though. Nice even wear of the cap here. I'm going to stop it at the end of this line. Okay. I'm going to drop the voltage down to 8. We'll do our relative rotate. I'm going to drop the current down to 30 picoamps here. It's looking about as good as I could have hoped for up to this point, so. All right, so just like before, we dropped the voltage, so let's do a modulator balance here, or a L2 modulator. Looks reasonable. Nice thing about this one compared to the gallium one is that when you pull the up and down, the horizontal up and down, it adjusts up and down movement. So that was a nice upgrade. Okay, so then can we, the stig looks pretty good here. Just go ahead and tweak this a little. Okay, looks all right. Okay, we'll go 4.5. And we'll drop this to 2. Okay, we'll make this a little bigger. So definitely at 8, the beam is not localized, okay, to the strap or the milling area. Okay, it's definitely going outside of that. Okay, we're seeing the bottom. That's not a problem though. We still have all this up here. It's going better than the one I did earlier, which was what I was hoping for. Okay, I'm gonna stop it there. Don't like stopping it in the middle of the line, but had to. All right, got a little bit of a hole down there. It's not really a problem. Again, we care about up here. All right, we'll do a relative rotate. And so our current, of course, is pretty low here. So again, we just need to singe the other side here. All right, where are you? Looking good. Nice and smooth. Okay, so yes, so this was going from 30 to 16 was giving me a better result here. And then to 8 rather than going from 30 straight to 8. Again, this is on the PFIB. Now, of course, if we wanted to, we could do another step on the other side. Take a look and see what we got here. So that drifted quite a good amount. Well, looks pretty good here. All right, we'll run one more step here. Or run one more line. All right, let me do the relative rotate here. And I want to cook it just a little bit more on the previous side. Not a whole lot, but just enough. And then we'll talk about what we can do at 5 kilovolts. Because I did have some success with that, even though the lamella didn't turn out great this morning. I did have some success doing some 5 keV thinning. All right, where are you at? Okay. All right, let's go 0.15. So now it's got some kind of mechanical hysteresis, so now it's shifting upward on us a little. All right, let's give that a shot here. Okay, so we're watching the cap here. We want to make sure that there's still a little bit of platinum left on the cap. There's still some room there, so I know we can thin this more. So at 5 kilovolts, the strategy is not going to really be to like do a lot of aggressive thinning. It's basically going to be just to kind of tickle it a little bit, right? Because you're talking about reducing a damage layer that's maybe 5 nanometers, 5, 6 nanometers to, 3 nanometers. Okay, so you don't have to do much to do that, to elicit that kind of an effect. This is looking good. Okay, I see the cap wearing down. And that's 200 nanometers of chromium on there. Okay, and I think we can let this run. It's kind of a game of chicken now. It's a game of chicken. Who's gonna win? Oh boy, we're gonna leave just enough on there. Perfect. Okay. All right. So now that's where we want. We've endpointed the thing. Okay. So now, if you want to go to 5 kilovolts, go to 5 kilovolts. We're going to go to 10 picoamps. So not much current here. Okay. Not much current. I suppose we should cut the other side first because, you know, that's how we've been doing this, alternating the cuts. So let me rotate. Now at 10 picoamps and 5 kilovolts, your milling rate is going to be very slow. So we're going to have a lot of control here. And again, you know, we're talking about removing a handful of nanometers here. All right, we're definitely going to have to check our all right, might be off a little bit. Okay, that's worse. That looks reasonable. Good. All right. And same thing, can focus. All right, so different approaches to this. I'm going to keep this box here, okay? And again, now the beam is very much not localized, okay, to the box, okay? It's not localized at all at this point. So let me just drop this to 1. I'm basically going to do maybe like a pass or 2 with the cleaning cross section and call it a day, okay? Again, we're just trying to, you know, barely scrape the side of the sample. We're really not trying to like macroscopically thin it anymore. I know it's kind of an, you know, makes no sense considering we're in a microscope, but okay, but by doing this at a shallow angle and keeping the current low, we should limit the, you know, any instability we get here. All right, so I'm going to stop it at the end of this line. Okay, right like that. Okay. Some people like to use the rectangle for this. I find that the cleaning cross section still gives a better result than the rectangle. But I've heard that you can do this with the rectangle. Again, I personally haven't found that to be quite as effective. but you know, to each his or her own. Whoops. Again, on this side, we have more stability with the milling. All right, and there we go. So again, I'm still at just 2 degrees of overtilt here. I'm keeping that very shallow. And once this is done here, okay, so that's it. All right, so that's a done lamella here. And as far as PFIB lamellas go, it's not too bad. All right, so let me do actual, we'll tilt back to 0 and take a look here at our handiwork. Now you don't want to do any ion imaging of this at this point, okay? That's a no-no. We want to limit the SEM imaging as well. Yeah, oh, that looks really good. That looks really good. As far as fib lamellas are concerned, I mean, that's definitely well under 100. I mean, it's hard to say exactly. We might be, pitched off a certain way here, but yeah, it's a good looking sample here. I mean, one thing we can do, because I'm definitely kind of curious, if we tilt to high angle here, we can see how this looks like the sidewall, if there's any roughening, curtaining, that kind of thing going on. I'm gonna switch to UHR mode for this. So I'm actually going to do 2 things. I'm going to drop the current, and I'm going to switch to immersion. Okay. So this is going to make it really easy to see. We'll turn on dynamic focus, assuming we're imaging the cross-section face, which we are. Check the crossover. And it's a little dark. Okay, I think we're okay though. Yeah. This can be tricky to do when the lamella is tilted like this, but we will soldier on. All right, lens modulator. That's definitely off. All right, then we can find something. Whoops. What did I do? Oh, I think I did degauss by accident. That's okay. Okay, what I meant to do is that. Okay, reduced raster. All right, that looks reasonable for now. I mean, really, as far as PFIB lamellas go, this is pretty good stuff here. All right, let me do a photo. I have this set to do frame integration. Yeah, I mean, really, it looks, smooth in the vicinity of the surface here. We got some stuff down here, but again, we don't really care about that. Let me testing. Whoops. Oops, my dynamic focus got turned off. Okay. Try this again. Doesn't really look much different. All right, and then what we can try doing, we can try measuring this edge on. So if we tilt back to 0 here, we don't need dynamic focus on for that. So the question is, where are we focused? So we want to be, all right, so now we're over focusing, that's the top. Now we're under focusing somewhere about there, I'm gonna say. I mean, depending on how, yeah, so we're definitely a few tens of nanometers, I think, based on what I'm seeing here. So, yeah, I mean, that's good. That's what we're hoping for here. I think, yeah, right about there. So I think it's definitely a success. Okay, so now if I have the time, of course, I want to pop this into the microscope, and we can see how it looks, right? So we'll pop it into the thymus, and we'll go from there. Put this back into field free. And yeah, so there we go. So new and improved PFIB lamella prep. So hopefully gave you some ideas, and let me know what you think. All right, happy February.